want you to do is, when you are done with this code, your code should produce some sort of diagram like this. And as you can see, there is a position in angstroms and energy in electron volts. That's how I wanted to plot it. And these are not SI units, so I do not want you to solve in these units because it's potential for error. So you solve in the energy in joules and position in meters, and then later on at the very end, when you get all the answers, when you're plotting, you can convert them to angstroms and EV to plot. Make sure you label your axis like this. You don't have to have these same spacings or tick marks, but at least label them properly. So what I want to also highlight here is that the way these are plotted is, for example, you can see the bottom of the well is 0 energy, and there is some height is 0.135, which is given to you in this problem. If you notice, this is 0.135 MeV, which means milli electron volts. Again, some of these numbers are given to you not in SI units. 1 electron volt is 1.6 times 10 to the minus 19 joules. So there's a big order of magnitude difference. So be aware of that. And when basically this is plotted, is what you will notice is that the wave functions you get will be of very different magnitude compared to the energies here. So what's being plotted here is actually not the wave function probability density, which is wave function magnitude squared, but some multiple times that wave function magnitude squared, this multiple A, plus that energy to shift it all upwards, because the wave function does go to 0 as it goes into the barrier. So this value, for example, for this red wave function is a 0, but it's not being plotted as 0, right? It's plotted as 0.0, close to 0.04 in this case. That means the energy is added on to this wave function, and there is some factor which you can randomly adjust so that the wave function looks good. You can make this factor 10 times higher and the wave functions will look very big, or 10 times lower. So this is just for you can call it aesthetics, or just for it to look good, so you can kind of see the wave function. But the actual magnitude on this scale, it doesn't make sense. First of all, wave function does not have the unit of energy, the magnitude squared. So we are just plotting them on top of this potential energy diagram to be able to visualize. So that's one thing. Second thing is that in the part A, for example, I have asked you to write a function for Schrodinger. You give the mass x and v. I just want to kind of reiterate what these x and v's are. X is a vector or an array in MATLAB, and for example, in this case, it could be 0, 10, 20, 30, 40, 50, 60, going all the way to 600 times 10 to the minus 10, right? But if you notice, that's a very sparse spacing of the grid. So that's what x is. X is the position vector. So 0, 10, 20, 30 in this case, going to 60. So I want you to make a variable in your code, which is the number of grid points in your total problem. So I can adjust. So I think I've written that down. So I can adjust, or you can adjust the number of points you have to take. So if you notice, suddenly the potential energy drops at this point. So if you don't have sufficient resolution, it won't capture this drop very well. Well, this is a sharp drop, right? It don't have to be sharp drop. When you discretize this, what's going to happen? You have potential energy. So V vector defines the potential energy at each of those x points. So for example, for x, if you have a vector 10, 20, 30, 40, 200, 210, 220, the V vector should look like 0.135, 0.135, 0.135, 0.135, and then suddenly 0, 0, 0, 0, and then 0.135. So, and times 1.6 times 10 to the minus 19, because it's in joules. And your grid spacing will kind of determine. So what actual problem you are going to solve is a straight line and then a slanted line from this grid point to this grid point. You will never get the state. If you make it your grid smaller and smaller here, you are mimicking sharper and sharper drop. You don't have to go very sharp. The more number of points you choose, the longer it takes for MATLAB to solve it. This is a fairly simple problem. Even if you take quite a bit of points, it should be. In general, you should not need more than 100 to 100 points in this whole region. I do want you to make equally spaced points. So that's that. And the final thing is, I do want you to read this problem carefully, and I gave you some notes. But in the end, if you look at this problem, what you're giving to this problem is, for example, look at this equation 4 in this attachment, psi1, psi2, psi3, psi4. So this is assuming you have 4 grid points in that problem. That's it. And psi1, psi2, psi3, psi4 are the values of the wave function at those 4 points. And in the end, you are going to give MATLAB this matrix plus this matrix, because it's basically H psi equal to E psi. So this whole thing psi. So you have to read this. In the end, what this becomes is like a kind of a sub-diagonal matrix. So there are diagonal elements in this matrix, and in this matrix there are 2 off diagonal, the upper diagonal and the lower diagonal, and the rest of the elements are 0. So when you create this matrix, you just give that matrix to MATLAB EIGS function, which I just told you, and it will give you the energies and also the wave function on those grid points. So I hope this is sufficient hint for you to, if you were stuck, or do you have any questions? I don't want to spend the whole time on this. That's pretty much I wanted to talk to you about. Even if you have done this, I think, anyway, let me just stop. Even if you have done this, it's good to go over this. But did you have any questions on this? Okay, if not, I guess I'll just get started. Don't feel, I mean, okay, let me not, I keep mentioning that you should have started your homework. I know a lot of students do not do it. Okay, so it's okay if you did not start the homework, or for some reason you're really in the beginning and you feel like, oh, I should not ask this question now. What's going to they're going to think, you know, I'm still starting out. Don't worry about that. Okay, I'm not going to hold that against you. If you have a question even in the first problem or just starting out, so I would rather have you spend time on it. I know I used to do it in the last minute sometimes, so it's okay, and it's always okay. So if you have a question now starting out, don't feel bad to ask questions in the last minute also. Okay, again, it's the goal of the course is not to penalize you or anything. It's just so that you learn, basically. All right.
I had a question then.
Yes.
We're given in the problem a lot of things in MEVs and non-SI units. Should I just convert them to regular joules first and then do the math, or should I?
Yes.
Okay.
Yes. In your code, that's what I want you to do. So just to learn, it's like in even research also. Make your code modular. So when you define all these the constants that are given to you in the problem, define them as constants. And then when you let's say I'm giving you 135 MeV, that should be some constant which later on gets used. So but in the top of the code, you just modify that constant, something goes wrong. So when you say 135, just define it as 135 times 1.6 times 10 to the minus 19, so that it's in joules. So that way you're making, I mean, I have had student like last year, similar problem I had. And even I remember students choose to do it and let it be in EV all the way throughout for different courses. That's fine if you want to do it. You then really have to make sure all the things which are energy remain in EV, and that could be tricky. You know, you could lose track of it or make an error. But when you're doing SI units, that's the magic. It takes care of itself. So all energy will turn out to be in joules. All distances will turn out to be in meters and so forth.
Okay.
All right. Okay, so I wanted to just finish off this section that we did last time of coupled quantum wells. If you remember, we did this problem of this whole big 2 quantum well structure, and we solved this basically assuming that we know the solution of this left quantum well individually. So we know the energy E1 here shown, and this psi left, we know this answer, and similarly we know right quantum well individually, so we know the E1. Turns out, since this right quantum well is the same as the left quantum well, they're both same solutions in terms of the energies. The wave functions are also same but shifted in position. Now we are combining these wells together, and so this becomes a double quantum well problem, and we found out that the energies were actually modified. The final energy was actually E1 plus some delta E, E1 minus delta E. And the wave functions were turned out to be actually this plus this, which was the bonding, and this minus this, which was the anti-bonding. So these are the solutions, if you remember. Okay, that's where we ended. So, and we call this minus, the psi minus and psi plus values, which is the lower energy is the -1 and the upper energy is the plus, just like a label thing. So, and so this is called energy splitting, and this is kind of a prelude to show you how bands are formed, and how energies change when they are very close to each other in coupled systems, coupled quantum systems. So before we move further to start talking about crystals, so these were 2 isolated quantum wells mimicking 2 atoms. Now what if we have infinite atoms? So that comes next. But before that, I wanted to talk to you about the time evolution of quantum states. So this is a Schrodinger equation right here, which let's say we solve in general to find stationary states, right? Stationary states mean there is no time here, right? This H is also time independent, everything is time independent, and we find some solutions which are En, E sub n, and psi sub n. These are stationary state solutions. What does that mean? If we initialize our particle somehow in one of these states, it will forever remain in that state. Does that mean the wave function will remain like this forever, psi n? No, that does not mean that. So for example, here is what I have written. So now I'm going to talk about this is going to be my stationary state wave function. Okay, okay, I'm going to write. So this is going to be my stationary state wave function, and this the other one symbol I'm going to use, which is called, I don't know exactly, this is the capital psi, I guess this is the small psi, Greek letter. So this will be a function of space and time. This will be time dependent wave functions. So how, if you initialize your particle in one of the stationary states, psi sub n x, that's what this means. The capital psi at time t0 is set to this one of the stationary states. What's going to happen at time t equal to t, 1 second or 2 seconds? Will it always, stationary state means the probability density, which means if I do a probability density, this value will remain the same over time. But the wave function itself does actually change. And so that comes from time dependent Schrodinger equation. And I kind of in the beginning argued about this, why this is. I'm not going to go over this, maybe just take it for granted. So the wave function with time, if you initialize in this stationary state, adds on this extra factor, e to the minus I, e, the energy of that state, t over h bar. So if you notice, this extra factor that's added here with time is only a phase factor. When you take its modulus, it's going to be 1. So you remember this Euler's function. When you take its modulus, it's 1, right? So when you take its modulus, its probability density, because this factor turns out to be 1, so the probability density always remains the same in a stationary state. Now, what if you do not? So is that clear? What if you initialize for this value at x time 0, initialize in not this stationary state, but sum of two stationary states, psi 1x plus psi 2x, or psi 1x plus half times psi 2x. And that's the real practical thing that happens all the time. You almost never are able to initialize in a stationary state a particle. And mathematically, have you seen any of this? Anybody knows what will happen mathematically? If I had this psi, capital Psi x of 0 as small psi 1x plus psi 2x, which means the first state plus the second state. And that's what's going to happen with time. Have you done this kind of a problem before? Or if you haven't done,
the question.
What?
I don't understand the question.
Well, if I say psi x of 0, that's at time 0, this is my particle's wave function, right? Particle's wave function does not have to be stationary state. And I say it is psi 1x plus psi 2x. Now my question is, what is the particle's wave function at any other time? Does that make sense, this question now? Does that make sense?
It's just the regular wave functions multiplied by the time operator, right?
But how? So because these are two different states. This one has energy E1, this one has energy E2. What's going to happen?
I think E1 will, the time operator will have E1 multiplied to it, and the second will have time operator E2 multiplied to it.
Right. So that's true. Exactly. That's what has happened. So Michael, I hope you got what he said. As with time, this wave function evolves, the phase of each wave function will change. But now, what's going to happen to this magnitude? Will it stay the same as psi 1x plus psi 2x magnitude? Because at time t0, that's what the answer was. At any other time, what will happen? It won't change. So I hope you'll see just that in the next page. When you initialize your wave function for a particle, so this capital psi with time is the wave function of the particle. Those small psi's are stationary states. Those are solutions. That's not, I won't say that's a wave function of the particle. Wave function of the particle is this. It requires x. It has x position of, it's a function of space and time. What's this wave function of this particle? Is it one of those solutions, or is it some of those solutions, or something else? It can be anything. If you put the electron in some place, it's kind of like a Gaussian function, just like or maybe a very sharp impulse placed in that location. So just as Ian mentioned, how I have written it down here. When you initialize a wave function, you can always expand it in terms of the stationary states. So that's this expansion. You can always find these coefficients a sub n, right? So let's say Michael chooses to initialize the particle with a sine wave probability density. Somehow he's able to do it. Well, put that sine wave here, sine of x, and that equate it to the sum of all the solutions, stationary states, and find all a sub n. So that's your coefficients that you found. And once you find all a sub n, for different state. So basically, you are finding what fraction of each state contributes to this initial state. Some first state might contribute to 90%. So these A sub n's are different fractions of how much they can. And then when you are looking at the different times, you multiply each one of those coefficients with their corresponding energies. And this gives you the time evolution of that state. So basically, the coefficients become function of time. But what happens in this case is you will notice, and when you solve this, and I hope you can see this also, because each coefficient has a different phase factor now. And when you take a magnitude, remember for complex numbers, a plus b, if two complex numbers, this is not equal to mod a plus mod b for two complex numbers, right? So when we take a mod of this whole summation, it's not going to be the mod of each individual. So these phase factors which get added do make a difference now. So
the phase factors only make a difference when the wave function is a sum of multiple wave functions. Okay.
Multiple stationary states.
Okay.
It won't make a difference for probability. If it's in the stationary, if it's in a when I say it's in a stationary state, it has to be one of the stationary states, right? It cannot be sum of two stationary. Then it does not, stationary state does not make sense. When I say it's in a stationary state, that means it's one of those states where it's initialized. So, and if you can initialize in one of the states, it remains there forever. So I mentioned some examples. As always, an electron moving through a semiconductor, when you put the electron in one of the part of the semiconductor. And another example I'll show today, an electron tunneling through a potential barrier or a quantum, just the same example that we did. So here is the setup of the problem. This is on your left top screen. This is the quantum well problem. So we have this two wells an electron can occupy. This is the problem. So there are two stationary states, psi minus and psi plus, and they have their corresponding energies, which are these E minus and E plus. And this is the psi minus which we found earlier, psi minus and psi plus, right? Now the question is, well, we are not initializing in psi minus or psi plus. If we were able to somehow initialize psi minus or psi plus, it will always remain in that forever. But what we do is somehow we are initializing the electron in the psi left, which is no longer the stationary state. So in other words, you can think of this as you're somehow, and this is a realistic situation. When you have a p-n junction, for example, you inject electron on the p side, and that could be a quantum well, and that there could be an n side, a hole on the n side. And there could be multiple quantum wells. So you could inject an electron through some electrical process. And that's how you initialize the electron in one of the wells, and maybe in this state. What's going to happen with time now? So I've kind of solved this problem. This will be your next homework. I think I should give this homework because this helps to understand this process much better. So I set my initial wave function as psi left. Okay, since psi left is psi minus plus psi plus, maybe you can see that from here. So this is psi minus, this is psi plus. If you add them up together, and again you can add them up together, and also yeah, I think, and then multiply by 1 over square root of 2 to take care of making sure everything is normalized. You add them up, you will get psi left back. Okay, that's what this shows. So basically you are initializing your wave function in sum of two stationary states. Does that make sense? When you put electron in the left well, it's essentially saying that you are initializing in sum of these two stationary states of this problem that we have now. And then after that, it's a mathematically simple problem to solve. At time t, this was time 0, right? At time t, you add these two different factors. to each one of those. One is E minus T factor, and one is E plus T. And then you can do the algebra and try to find the probability density. And what you will notice is that the electron sloshes back and forth. You can plot the probability density with time. It is sometimes in this well, and then it's in this well, then this well, and this well. This is called this is called tunneling, and it's also called, the oscillation is sometimes termed as Rabbi oscillation, although Rabbi oscillation is used in general for something else, which is when you shine electromagnetic radiation. So the photon gets absorbed and emitted and absorbed, and so this is how photons get emitted from atoms or molecules or quantum wells. This is a stimulated radiation process, and that's where these are also called Rabbi oscillations or sometimes Bloch oscillations. But this is also can be termed as Rabbi oscillations. But think of this as basically electron sloshes back and forth. You can see with time, and you can also think of this, well, this electron is tunneling through the barrier. Even though when you put this electron in this well, its energy was E1, there was a barrier which is of much higher energy. And how is it possible that the electron can be found in this second well sometimes? That's the quantum mechanics for you. Your particle can tunnel through barriers even if it does not have enough energy. And there is a specific frequency of oscillation you can find. So I'm going to show you a movie for something that for example, the lasers that we build in our group, they are kind of based on this principle. So here, these are two wells I'm showing. These solid lines and the dashed lines are basically two of the stationary states for each of these wells. So I'm not plotting the solution of these final combined two wells, and they are tilted because an electric field is applied to them. So this is a specific problem where you tilt them enough, you apply enough DC electric field that number one state of the previous well is same energy as number two of the next well. So this is a way tunneling happens, tunneling electron or hole transport happens in semiconductor quantum point contacts or quantum wells or quantum dots. And when you put an electron in this well somehow, let me show you how things happen. And this was one of the simulations that one of my colleagues who used to do theory did. You can see the electron was first initialized. So let me start the movie again. So here, let me pause it. Okay, the electron was first initialized in this blue state. This is not a stationary state of this whole problem. This is a stationary state of only the left well. Since the electron is initialized in this state, which is not the stationary state of this whole problem, it evolves. And by evolving, it means with time, this probability of finding the electron in state 2 increases. And you can see it goes back and forth, but you are also seeing one thing. It goes back and forth, and the electron actually, the probability of finding electron in this one state increases, and over time, electron kind of settles in this state. So there is something else going on in this problem. And this electron, as soon as the electron moves to this well, it can also scatter through some process such as Phonon scattering. So that's implemented in this code. So in a semiconductor, there are always phonons, and it can lose its energy and fall back into a lower state if a state is available. So what happens, it tunnels back and forth few times, but it's also relaxing to this lower state. But every time it tunnels into this well, it relaxes. It loses some of the electrons, relaxes. Some of fractional probability relaxes. And within some time, within picoseconds, it completely settles. And if there is nothing else in forward, it just comes here. So you release an electron here, it eventually moves to the next well. So this is an electron transport. This is called quantum transport. So a more advanced course in semiconductor physics of quantum transport will actually solve some of these scattering, do scattering calculations to compute. But this is how essentially quantum transport happens, as opposed to classical transport, which we learn in ECE451, for example, which Michael may have taken, and which, for example, if you might recall, we use Drude model to model. We will actually not go into quantum transport in this course. We'll cover aspects related to it, and I will cover some of the Drude transport again toward the end of this course. Because to be honest, when you do theory or condensed matter physics, and if you are doing theory of transport, then only you do these kind of calculations. Not everybody who's doing research in experimental physics needs to do such calculations. Okay, so that was for time evolution. Any questions here? Let me just bring this up. Don't worry about these, some of these parameters which define some of this transport. It's related to what I do. Just a minute. No questions?
I have a question. I still have a little trouble understanding what a stationary state really is. What really is it again?
Stationary state is the solution of time independent Schrodinger equation. So let's say your problem actually, so for example, your 2 quantum well problem is a time independent problem, which means the quantum wells are not changing with time. When you solve this problem, the solutions are called stationary states. Okay, those are the solution of the Schrodinger equation. But that does not mean the particle does not change with time, or its probability does not change with time. So this is, yeah, I can see where the confusion might be coming from. You can have a time independent problem, but the particle can still change with time. That will happen if you do not initialize. So this is based on initial conditions. If you do not initialize the particle in one of the stationary states. So in other words, if you have a problem and you solve it, it does not mean the particle will be in one of the stationary states. Somebody has to establish that particle in that stationary state, and then it will remain in that state. It's a solution. It's one of the many solutions. Those stationary states, all of them are solutions. But who is there to tell you that which energy state does the particle occupy? Right? You find energy 1, E2, E3, E4, E5, E6. We always do that. We find infinite energy levels of a square well. What does that mean? That means that the particle can be in any one of those states. Who decides that? That's the person who establishes or initializes that particle in a state. But if you do not initialize in one of those states, then the particle will not be found in it. It just keeps changing with time. Does that make sense?
Yeah. So yeah, I think so. With a stationary state, do stationary states, when they evolve in time, evolve according to the
stationary states do not evolve in time.
Okay.
Stationary states do not evolve. They are just solutions of the problem. What does evolve with time is the particle's wave function, and that particle's wave function is dependent on how dependent on the initial conditions or the boundary condition, you can say. So particle's wave function is a singular function, psi x of t. There is no energies in there. There is no E1, E2, E3, E4. It's a wave function of a particle.
Could you write out what the stationary state is in the wave function?
Okay. Okay, so So these are stationary states, and they have corresponding energies E1, E2, E3. And the particle's wave function is this, psi x of t. So the difference is I'm using capital psi versus these are small psi, where I'm not using that. I mean, some people can use this kind of a psi and then this. So those are two different symbols. So I'm not, when I write like this becomes the capital psi. So this is the total, you can say, this is the space and time dependent wave function for the particle. So when we say this is the wave function of the particle, in fact, since it's changing with time, the particle's energy is also changing with time. The energy is no longer strictly defined, right? So just like Heisenberg's uncertainty principle, you cannot really define energy of a particle strictly when it's evolving with time. If it's not in one of the stationary states, you cannot tell what its precise energy is. I'm wondering how physics instructors tell about this concept.
I think I would call them just eigenfunctions. I think that's what you're trying to say.
Well, yes, so stationary states are eigenfunctions, but this time-dependent wave function is not an eigenfunction. Time-dependent wave function is the solution of the time-dependent Schrodinger equation. It's just a solution of that one equation. And it's not an eigenfunction, because eigenfunctions are solutions of the eigenvalue equation, which is time-independent Schrodinger equation.
Okay.
I have a feeling, and if I remember, I mean, I have not taken a graduate level quantum mechanics course. Actually, I took a engineering version of it. Actually, I did take it, but most of the quantum mechanics that's done is done with stationary states. So there could be, this confusion could be due to that, because they do not really do that much of anything related to time evolution. That comes usually in physics, condensed matter physics courses, when you're doing quantum transport. So they don't even mention this too much. They don't deal with time-dependent Schrodinger equation too much. And that's why this may be leading to some confusion. If you still have questions, you can maybe discuss with me later, okay?
Okay, that sounds good.
All right, so let's look at our Schrodinger equation back to it again. And now we are moving to crystals. So originally, this is our time-independent Schrodinger equation. So now we are not talking about time evolution, okay? So let's throw that out of the window. We are now again interested in finding stationary states for electron in a crystal. So when we write this kind of an equation, so first of all, this is an interesting thing. What we are trying to find out is, we have all these atoms in the crystal, to be precise, of the order of the Avogadro's number, which is 10 to the 23, right? Avogadro's number is number of atoms per mole, or you know, on that order, it could be much more or less, but of that order. So 10 to the 23 atoms per centimeter cube. That's kind of an order, you can say. And all those atoms contribute to this potential energy. So it's a periodic potential. Think of each atom having a nucleus, which is positively charged. And then all atoms have electrons. Now, if we assume those electrons do not exert any force on each other, any energy, there is no potential energy due to electron-electron interaction, and they do not collide and they do not affect each other's motion, what we can assume is that there is one electron, each electron can be treated independently. And this electron is seeing these positive nuclei placed periodically in the crystal. And what will the energy of this electron be? So that's this VR. This VR is a periodic potential. In other words, this VR is periodic. So VR is equal to VR plus Rj, whereas Rj is the direct lattice vector, any direct lattice vector, so written in this form. So this is direct lattice, which is L times A sub 1 plus M times A sub 2 plus N times A sub 3. A1, A2, A3 are the primitive lattice vectors of the direct lattice. So this is a periodic potential because of these atoms, and we want to solve this problem. If this VR was only of that one atom, we already know the solution. That's the, you can say that's the hydrogen atom solution. Obviously, those solutions become a little more involved, different when you have a multi-proton nucleus. They become slightly different, but still hydrogen atom solutions are quite accurate, even if you keep increasing the atomic number, right, in the nucleus. You just keep on increasing the charge. So those solutions I showed you a couple of classes before. They're the s orbital, the p orbital, 1s, 2s, 2. Those are the wave functions we can find. Now we have this VR due to the crystal, and how do the wave functions look like for this periodic problem? So a few things, some notes. This del square is the, I think it's called the Laplacian, if I keep forgetting the operator, which is del dot del operate, and this is an operator, so this is not a vector anymore because it's a dot product of dels, and it's del square over del x square. In Cartesian coordinates, it's just written like this. So it's a second order differential in Cartesian coordinates, and this potential is periodic. So qualitatively, I showed you a picture of how bands are formed in silicon. This is another picture of the same thing. If you had an isolated atom, this is how energy levels look like. First level, 1s2, 2s2, 2p, 2px, 2py, 2pz, those are degenerate and so forth. These are sharp energy levels in the sense they are precise energy levels. Now, this is an isolated atom. When you bring lots of atoms together and bring them closer and closer and closer, the lowest levels still are sharp. But what happens? If there are 10 to the 23 atoms, there will be 10 to the 23 states. They will have exactly same energy right here. 10 to the 23 here, 10 to the 23 here, 1s2, 10 to the 20, 1s, 2s2. There will be same energy, but they will have each different wave function. One wave function will be localized on atom 1, the s orbital. One will be localized on atom 2, the s orbital. So think of these as many quantum wells, and final solution still is localized states because they are not close to each other yet, and they do not interact. So you can find each of these, so you can find each of the wave function for this crystal is still those 1s orbitals for located at each atom. Does that make sense? So in other words, they do not split, they do not change. In our coupled quantum well problem, the psi left and the psi right, they do not mix with each other because the quantum wells are far away. The final solutions will still look like psi left and psi right with the same energy. So those are called sharp or discrete levels. They haven't changed. But as you go to higher energy levels, this starts splitting. So this splitting is the same as what we saw in the coupled quantum wells. The closer the quantum wells, and that's what you will see in the homework problem. The closer you make to the quantum wells, this energy splitting is increasing. Okay, and there will be these 10 to the 23 levels, each closely spaced, and they form bands. So there are some bands and there are some gaps where there is no energy levels, and bands again. So this is the energy band formation, and we want to see how that happens, and we want to also see these are the energy levels. What are the corresponding wave functions for such a situation? So here's just a calculation at what's the typical atomic spacing for silicon. The large cube size is 5.43 angstroms. It's a diamond lattice, and in a diamond lattice, the nearest atom to atom distance is the diameter divided by 4. You can go look back in the diamond lattice. So diameter of this large cube, which is square root of 3 times A. And so when you calculate the interatomic spacing, which is also called the I think it's called a monolayer, or 2 times the monolayer, I forgot. But that's 2.35 angstrom in silicon. So one thing to notice on this slide is that the electrons in those energy bands, what we are interested in finding out what those energies will be, and also what the wave functions will look like in these bands. The wave functions in these discrete levels will look like exactly the same as they are of the atoms, just shifted to each atom at its own location. The wave functions for these bands will be modified. But how are they modified? If you notice, the energy levels that do get modified are those are called valence states. And the valence states, usually for the semiconductors at least, not for metals or insulators, those are typically the most common semiconductors. Those are the S and the P states. So one thing I want you to remember, the nature of the wave functions of these conduction band which is formed and the valence band, those are the two bands of our interest that's formed. These are formed from S and P states. They do retain some of the geometric shape. So we can say they retain the character of S and P orbitals. Okay, so that's something for you to remember. For example, in gallium arsenide, the valence bands have more of a P character, and the conduction band has more of a S character, and they are more of a spherically symmetric. So we will find that out later. Okay, so here's an example of how our VR, the potential. So again, remember this V is of the units of joules, energy, not voltage. Okay, just a minute. So you can, what is this? This is on the top right. This potential is due to a single nucleus. So remember, the potential will be of this form, right? Q square over 4 pi epsilon r in spherical coordinates. So r is the distance between the nucleus and the electron. So if you're trying to solve for an electron, so this Q is the charge of the electron. So this is for, let's say, hydrogen atom. So it goes as 1 over r. So that's why this is plotted as 1 over r, right? And the location of the nucleus is at r equals to 0. Well, this is written as x. It should be here. You can say this should be r, radial distance, right? But we are going to kind of argue in terms of one dimension and think of this problem as written in terms of x. So when you put those atoms at the periodically with the periodicity of the lattice, this is what VR might look like. And these blue lines are the energy states once you solve them. And you have to just realize what's being drawn. Sometimes it can be confusing. For example, this blue line and this blue line, that means energy is just a value, right? This is a straight line going through the whole thing. So this is one energy. By drawing it like this, what it means is all of them have same energy, but the wave functions, there are multiple wave function solutions. One is localized here, one is localized here, one is localized after you solve it. But in this case, the wave function is actually localized in the whole. Once you reach the valence states where the energy gets modified, wave function is no longer localized to one atom. So this is the biggest change that happens for the valence states. These are called valence state. By the way, conduction band and valence band, the energy states in both those bands are due to valence states. So there is this a bit confusion. Valence states are the states which are the higher, not completely filled states in atoms. Those valence states lead to creation of bands, and we call often the band which is mostly filled or completely filled in semiconductor 0 Kelvin as valence band and other as conduction band. So there's this confusion, but the bands are formed of valence states. So these are valence states, and the electrons in those states, their wave function is no longer localized for one atom. It's actually localized in the whole crystal. So this is the most intriguing part of this solution. An electron which has an energy in the conduction band or the valence band, its wave function is spread in the whole crystal. In other words, that electron does not belong to any particular atom. Its probability of finding that electron is the same everywhere. It's kind of confusing because we don't really deal with those electrons. We deal with electrons which we initialize, or in other words, we inject somehow electrically or do. And those electrons can be initialized, but they move along the semiconductor because they are not the stationary states. So this will, I hope this gets more and more clear. This is fairly complicated. I mean, even I was a bit confused, and I still am. For example, I can, if you go and ask somebody about the true difference between the states which are deep lying states versus the valence state, how the wave function look like, people will still be confused and not be very specific in their answer, because it turns out the wave function for this electron in the valence state is actually spread in the whole crystal. So what does it mean? That you can actually never pinpoint and measure a single electron. They are everywhere. As soon as you try to measure some electron, you're actually localizing that electron by whatever thing you're using to measure that. So if you're using some electromagnetic radiation or some other microscopy tool to measure the electron, you are actually end up isolating those electrons around that atom. So you are no longer measuring the electron in its two stationary state. So it's an interesting thing. But let's move forward and try to understand how to find the wave function. So on the top is a diagram of a random potential energy, not periodic. So non-periodic potential. When you have, let's say you give this non-periodic potential to this MATLAB program that you just will write for this homework, and you find the wave function, this will be some weird wave function that you will find. Okay, some function of space. But if you, in your MATLAB code, if you give this periodic potential on the bottom of your screen, you can actually test out. Once you write this code, you can actually not only make two wells, but you can make multiple wells and solve for it. And you will find, interestingly, but not surprisingly, that the wave function is also periodic. Not the wave function, the probability density. So magnitude squared of the wave function, or magnitude of the wave function, is exactly periodic with the same periodicity for all the solutions that you find. Not surprising, because it has to be due to symmetric consideration. The probability of finding a particle in such a potential which is periodic in space must be periodic. Why should the particle be more likely to be found here than here? So it is, a probability is a periodic answer. What Bloch's theorem says is the following, and I'll repeat that. It says that the wave function, when you find the solution of the station. So again, remember, we are not talking about time dependent here. We are only talking about stationary state. The stationary states are periodic. So this u function is a periodic function. In other words, this u of r is same as u of r plus rj. Rj is any direct lattice vector, right? This is called a cell periodic function. Cell periodic function means periodicity with the periodicity of the unit cell. Okay, this is called a cell periodic function. And what Bloch's theorem says is that the wave function of the electron, when you solve for it, must be the cell periodic function times a phase factor. And so we will argue now where this phase factor comes and what does this k mean. Okay, so that's something which we will argue next. So there is some arbitrary k that we use. There's an arbitrary k that we use to describe this wave function. So that's why you see a subscript k. This is like a label. You can call it like a label. But the nature of the wave function, Bloch's theorem does not solve the problem. It only gives you the nature of the wave function, how it should look like. It has a periodic part and a phase factor. Okay, so let's start looking into this Schrodinger equation. So we have our Schrodinger equation that we want to solve. This VR is the periodic potential, which is the crystal potential due to all atoms. Okay, what does that mean? This VR is periodic with the periodicity of the lattice. Okay, so we want to solve this problem. Now, incidentally, turns out Laplacian operator is also periodic with you can say that it is also periodic with periodicity of the lattice. In fact, it's periodic with any periodicity. What that means is that because Laplacian operator, it operates onto somebody, some function of space. So if it operates onto a function which is periodic with the periodicity of Rj, you will get the same value. That's what it means. So then I can also say that this Laplacian is also periodic with the same. In other words, this whole thing, we call this Hamiltonian, is periodic with the periodicity of R sub j. So in other words, this Hamiltonian is periodic with the periodicity of R sub j. So here is the proof. If this Laplacian acts on a function which itself is periodic with periodicity of R sub j, if you take its derivative, since that function is periodic, obviously the answer will come out to be the same. So this left-hand side, this side right here, will be equal to right-hand side. So that's what this means, that when it acts on any periodic function in space, it gives you the same result. So that's not. So I mean, this is kind of maybe need not even be stated. So what I want to take so far from this is this Hamiltonian that appears up here. This whole Hamiltonian is periodic with the periodicity of the lattice. So for this is a differential equation, right? And I guess this is a hand-waving argument. I don't know the mathematical reasoning behind it. And I'm not sure if Bloch's theorem, the way he proves, also has a mathematical reasoning behind this. But this is the, so I don't quote me on that. If you have a periodic Hamiltonian, so you have a periodic Hamiltonian in a Schrodinger equation, your probability density must also be periodic. So This is intuitive, but I don't have a mathematical proof. But the probability density, if your potential is periodic, probability of finding a particle should also be periodic. Okay, we start from that. We start from that assumption. If the probability density is periodic, that does not mean the wave function itself has to be periodic, which means this wave function at another lattice site, the value of this wave function at another lattice site can be different. It does not have to be same. And in other words, it could differ by a phase factor. And that phase factor can be any function of Rj. So this within this assumption that I just wrote right here, this is the most general form of the wave function we can write. It can have a, because when you take its magnitude, this phase factor will go away. And this could be some random, some unknown function of R sub j. Okay. Hope this makes sense. This kind of an argument makes sense. So now the question arises, what should this function be? So this is the argument we, so it's kind of like a pseudo proof of the Bloch's theorem, or argument for why the wave function should be of this form in this page. Okay, these are called the Bloch's wave function, or basically it's a theorem that says the wave function of the electron in a crystal must be like this. So let's move on to the next. Let's argue. So I'm going to, that's why I'm not writing this, because you know, we can just go over this and you can look over this again if it makes sense to you. This it's not a big deal if you skip over this, but it's a good idea to know where this is coming from. So let's assume that we have this arbitrary phase factor, which we don't know yet what it is. Now let's do an exercise. Well, if we have Rj1, some lattice vector Rj1, it can be then written like this. Now let's add another lattice vector Rj2. So we are still moving within the direct lattice. So we now have psi of R plus Rj1 plus Rj2. So if our wave function is of this form, we can write it in two ways. One way is this, because you can kind of assume that this is some other direct lattice vector. So you just write f, because this was our assumed form. So f of that sum of two lattice vectors. And other way could be that we could write it as psi r plus rj1 times e to the I f rj2. Right here, right? You can take this on the left hand side and you can split it up for just the rj2. And then you can split this thing again, and that gives you psi r e to the power I f rj1. And then you also had e to the I f rj2. So that's where this is coming from. The one on the right hand side. So when you do it in two different forms, you get two different forms of writing it, right? Because the exponents get added. So in other words, that must mean that your f of rj1, whatever that function f was, f of rj1 plus rj2 must equal f of rj1 plus f of rj2. So this function must be of this form. If that function must be of this form, this is only possible for a function which is linear in position, linear in x or r. So if this is a function of f is a function of position r, this this property is only possible if this is a linear function, because you're this is how you define linear functions, right? When you when you have, if you have f of x and if you have f of 2x, then the thing goes as 2x. If of f of x plus y, then there is a linear coefficient for whatever that you're applying. So in other words, f of x must be of this form, some coefficient c times x plus d. So in other words, this f of r that we are trying to seek must be of some form, some constant times r plus another constant. We can kind of throw away that constant. We don't want that. I mean, that will be just adding another constant factor here. We can just assume it. So in other words, what I hope this exercise, what I have argued here is this f of r that we were trying to find out what this f of r in this phase factor must be. It must be of this form that it must be of some form that constant times r. So we can call that constant c or a or anything we call, and it's a vector. Since r is a vector, that constant could be a vector, a constant vector also, and then a dot product, we call that k. So just think of this as, and we choose k because k is traditionally used as a wave vector, and this whatever constant that appears here must be of the unit 1 over distance, because whatever goes, this function f must be unitless, right? Anything that goes in the exponent must be unitless. So this coefficient k must be of the distance of 1 over r, first of all, and then it's some constant coefficient. So we just call it k because k wave vectors usually are, we know that are inverse of distance. So we start calling this function as k dot rj, this function right here. What is k up to this point? Any constant. It doesn't matter what k is. But what we have just shown here or argued that based on this assumption that the probability density must be periodic, that the wave function should be of this form, this specific form with some constant k. So any questions on this argument so far? Basically, we are reaching close to justifying, I wouldn't say proving, but justifying Bloch's theorem. And this is also often written as one another form of Bloch's theorem. Remember, Bloch's theorem is written in this way. Psi is u, the sum cell periodic function times e to the, but it can also be, so it can also be written in this way. Psi, and I am going to put this k here just in case. I'll tell you why we put that k as a label here. Another way of writing the Bloch's theorem is this. Okay, so this is another way of writing the Bloch's theorem. So let me just move this down a little bit. There are subtle differences here. So you know the r that goes here in this is the one of the lattice vectors. Okay, any lattice vector. In this form, this is the space position vector r. Okay, so they're quite different, and not to get confused, but these are two different forms of Bloch's theorem. Okay, you'll encounter them more as we go along.
Why do we ever use the lattice vector, the capital R, if it's going to be if the wave function is going to be the same everywhere?
The wave function is not the same everywhere, right? So wave function at, for example, wave function, let's say you're sitting on a lattice point. The wave function at a lattice point neighboring to you, this wave function which is neighboring to you, is this value times the wave function at your place. So the wave functions, the value of the wave function at each lattice point differs. Wave function right here, is different from the wave function next to my lattice site, or the next to, by e to the ikr factor.
Okay, I see.
Yeah. So wave function do differ by a phase factor, not in magnitude. The magnitude are the same. When you take the magnitude of the wave function, so for example, you're sitting on a lattice site, Michael is sitting on a lattice point site, on another lattice site, and in between you, the wave function is some other value, right? It's a psi of r. It's changing with position. It's some other value. And if you go exactly one lattice site beyond that, so middle of the next neighboring lattice site, it's going to differ by the phase factor. But the value of the wave function at your location and halfway down to the next site, their magnitude also changes. So in other words, look at this diagram. The wave function here is different. As we are going somewhere, the value is here, it is different, value is here is different. And then the next lattice site, again, it becomes the same, the magnitude. So, so there is periodicity in the magnitude with the lattice constant, but the phase factor keeps changing.
Okay, so the phase factor is just the amount, like it's just the same thing but shifted over the amount. So
amount you move. So if you move one lattice site, that Rj will be 1A1. If you move 100 lattice site, that will be 100A1.
Okay.
So this
like,
RJ, and that phase factor also changes, right?
So it's like shifting. There's like a sine function, like 2 pi in one direction, another sine function, but it's just shifted over.
It's not a sine. Yeah, it is shifting over, but there is this k value, and this k is arbitrary so far. So you're not actually shifting by 2 pi's. Okay. You're shifting by some arbitrary phase, and you can pick this k so far, anything to any value. Okay, I think we are out of time. Is that okay? I'm going to take like 3-4 minutes extra here. I just want to finish this train of thought. Okay, so this is the outcome so far. Michael, you're still here?
Yes, I'm still here.
Okay.
Oh, sorry, I didn't realize my camera got disconnected.
That's okay. Is it making sense so far?
Yes.
Okay. Yes. Okay, so now now let's talk about what this k is. Okay. I guess I have written a little more, and maybe you can read. A little more. But what I would argue is this k is a parameter that defines our wave function. So let's say Michael chooses some k, any vector k. Don't think it has to be of the units. Remember, this k is a vector, just like velocity is a vector, right? Velocity vector has a units of meters per second. This k vector has to be of the units of 1 over meters. That's all you need to do. So let's say Michael chooses a vector k1, Ian chooses a vector k2. The wave function that Michael gets has this property right here on the top. The wave function that Ian chose has this property. But this wave function that Michael chose and Ian chose, they are not same because their properties are different, right? So both are solutions, both are possible solution to our crystal lattice problem, but they are not the same wave function. So you can say that for each k vector that we choose, we have a different solution. So those solutions are distinct. You cannot pick arbitrary k and just say I have the same wave function. So in other words, it's better to put the label as k with the psi, because it tells you that I'm working with k1, and this my wave function corresponds to k1. Does that make sense? So this K1 is a label, just like we for our infinite square well problem, we had label 1, 2, 3, 4, 5, first state, second state, third state. So you can call it like you have all these solutions which are K1, K2, K3, K4, K5, all the way to whichever K you want to choose. So that's why we start using this label as a subscript, psi sub K. Okay, because psi sub K1 will be different than psi sub K2. They're not the same thing. So that's about, I haven't yet talked about what K can be yet. Okay, we will come to that later. And everything is very precise, very specific, and very subtle here. Okay, you cannot just throw in, okay, K is some wave vector for, where does it come from? We have to always look at that, its origin. So far, K is just some vector of units 1 over distance. It's a label. It has to be a vector, and we can use it as a label. Okay. Now here comes the question. So far we have found this solution. But this does not tell us what psi K should be like. Should it be a sine function? Should it be a cosine or a Bessel function? Or what should it be? So what should it look like? So let's call it, let's say it should look like f of r. Okay. Let's argue. Should it look like a function which is periodic with position? No, it cannot be. Because if it was periodic with position, this on the left hand side would exactly be equal to this on the right hand side. So this phase factor should not be there. So in other words, this wave function should be of this form, where you have e to the I k dot r times a function which is periodic with lattice. Now, I may not be using the best words to describe this, but I encourage you to read this and make your own opinion what I'm trying to say. The question I'm posing is, we know this now so far from our arguments, but what should be the nature of this psi? What kind of functions satisfy this relation? Well, we can argue if this is a periodic function in Rj, that cannot satisfy this, because where does this come from? So it has to be of this form. So in other words, psi k of r, I'm looking for a function of r, position r, must be of the form e to the I k dot r and some f of r, where f of r is a cell periodic function, and instead of f of r we call it u of r. So we must have this. So yeah, this is the best I could do. You can try to read it or try to make sense out of this. The nature of this function to satisfy, remember this is a capital Rj here, this is not small r. To get this kind of relation, we ought to have, this is the only way we can have it, otherwise it's not possible. Okay, so I'm just erasing this because I've already kind of written this over. So this f of r is, traditionally the books use u of r, which is the cell periodic function. So coming back to this psi k must be e to the I k dot r times this u. Again, we use a subscript k of r. So, and sometimes some books use this or some books don't use it. It depends on how they define this normalized. Not all books will use this explicitly. I think even in this notes there is some confusion. The notes that Rana has written sometimes. So I will point this out. So this V is the crystal volume. Okay, you can explicitly write like this, and what that means is when you integrate the magnitude square over the whole crystal, because wave function exists over the whole crystal, and its value is 1. So I guess I'll start from this page next time. So this is the nature of the wave function of an electron in a crystal. We haven't solved the UK yet, but whatever we solve, finally our answer must be in this form. That comes from Bloch's theorem. Okay, so we'll carry on from here. Read this, it's pretty dense in some sense. I mean, it's also lucid, but it's dense. So as always, just go through this again, and I'll post this and read next 5 or 6 pages of the notes and try to make some notes and ask questions. We'll go over this next time.